Okay, good. Hello everyone. For this class, the Bioreactor Engineering. So today we will continue on our lecture. So for this one is is Bioreactor Engineering. This is lecture number 3 already. So in this part, we will talk about physical processes. It is fluid mechanics and mixing. And chapter 6 is heat transfer. And the chapter 7 is the mass transfer. This is for fluid. Shear rate is equal to viscosity and then dv by dy. This is velocity and then this is a distance. And this is for heat transfer. Q is heat, Ka dt by dy, and this is for mass transfer. The driving force is different. This is velocity different, this is temperature different, and this is concentration difference. And I think today I will cover only the fluid and mixings. And now we come to the part that we know a bit more about bioreactor, which is this one. Is transform the reactant, that this one. Is transform our reactant to the products like this. This one is called this one. And in the feed we have steam. Steam is for heat exchanger medium, which is the green one, and we have air supply. Sometimes we need to supply the air to increase the oxygen transfer. We will cover on the part of the mass transfer. We have to remove the heat, which is the second part of this one. And of course today we will deal with the medium, which is called the fluid. Fluid inside the reactor can be liquid or the gas, which is this one. And we can supply to adjust the pH. Sometimes we need to measure something. In the modern world of bioreactor, we have sensor to check temperature, aeration, pH, and we need to control the air supply, pH, which is we need to feed acid or base to the system. We measure the pressure inside, because sometimes when we do the culture or the CO2 is formed, so we need to remove it, or we need to look at the pressure, and we need to increase the mixing using this agitator system to mix our ingredient together and then something like that. So I think up to lecture 3 we know a bit more about bioreactor already. So but for this lecture I just focus on the something is called fluid mechanics. So wait, let me see first. And today we will cover the fluid plus, which is allow this one, classification of fluid mechanics. This is the content for today. Fluid in motion, viscosity. What we're gonna talk about is what is Newtonian, what is non-Newtonian, the factor that affect viscosity, because viscosity is very important for the culture of the inside the bioreactor, because most of it is fluid. So is if your fluid is more viscous, we need to choose propeller for example. Okay, fluid can be classified as compressible or incompressible. Okay, when you say about compressible, is can be compressed, such as gases, something like that. And if most of the liquid is called incompressible, because density of the liquid is independent of the pressure, different from this compressible one. The gas, the density is depend on the pressure, okay, and the opposite one is called incompressible. You can just imagine that fluid is like liquid, something like that. It's culture media, and if the gas is compressible, for example, fluid can be classified as compressible and incompressible. Okay, for this one, it's just the term you need to know about it. Or sometimes you need to focus on in viscous or viscous fluid. Okay, the ideal or perfect fluid, the ideal one has zero viscosity. Is never happen, right? This one is called in viscous. Okay, but the real fluid is viscous fluid. Okay, for this term, the ideal one is the in viscous. The real one is viscous. Okay, every fluid need to have some value of viscosity. Okay, for this term. And again, this one Newtonian or Newtonian is in next section. When you talk about Newtonian, okay, you can apply the Newton law. Shear rate E is equal minus mu is viscosity and dV by dy. Okay, viscosity is very important aspect for liquid inside the our bioreactor. Okay, and this one is the new viscosity. This one is shear rate. No, this one is shear stress. Shear stress is y-axis, and this one is shear rate. Shear rate is dy by dt. If you plot about two graphs, this one shear rate and shear rate, this one, and then shear stress in this axis. And if you got the straight line like this, the fluid is called Newtonian fluid. But if not, you can call the other things. Okay, we have different fluid. The first one is Newtonian. You for shear stress and shear rate, and then you got the straight line like this, is called Newtonian. But if you have this correlation upward, but it's not the straight line, it's called pseudoplastic. Okay, this one is Bingham. Bingham is straight line, but it's not past the origin. Okay, and this cousin plastic is similar to Bingham but different. We have some correlation like this. Okay, fluid can be classified as Newtonian and non-Newtonian fluid. What I skip is this part is Reynolds number. Reynolds number is the what is called dimensionless number, and this one is Reynolds number inside the pipe. The diameter, U is velocity, density, and this is viscosity. But inside the bioreactor, you can notice that it has some stirrer here, impeller, propeller, for example. We call it as the impeller Reynolds number, Ni di square. This is the same density and viscosity. This is impeller. This is diameter of impeller. This is the speed of that one. Okay, but for the overall unit is dimensionless, and you can notice that for the laminar flow, the Reynolds number for the impeller is less than 10. It's different from that from the flow in the pipe like this. This classified as this number. Laminar is the number is less than 2000, and transition is between 2000 and 4000, and more than 4000 Reynolds number in the pipe is called turbulent, but different from the Reynolds number in the impeller, because we have different kind of system inside this thing, inside the bioreactor. Okay, viscosity is okay. Newtonian is this one. This one is pseudoplastic. Dylan, Bingham. Dylan is where is it? not in this one, but you can imagine that if you talk about Newtonian is related to the shear stress and shear rate, and you have this kind of graph before, and then the other thing is called non-Newtonian, but it's different name here. Diagram is not written here, but it's not going to give this kind of correlation. Okay, this is example of Newtonian. Water, for example, can classify as a Newtonian, but if you have rubber solution, pulp, paint, this is called pseudoplastic. Bingham, you have some soap, cooking fat, grease, for example. Blood is cotton plastic, okay. Tomato sauce, juice, okay. Chocolate, okay. You have this kind of example. But if you talk about the water, it can be classified as a Newtonian. Again, this one is classification of the when you have the fermentation culture, something like that. Is called if you ferment the alcohol, you use this kind of yeast. Saccharomyces is Newtonian if you use very less solid solution is 10% solid. For example, you have Newtonian property, and above that 10% is pseudoplastic. Okay, you can have a look on this one. This correlation again, and you can notice that most of the thing is not Newtonian. No, I'm talking in Thai. Except for this one, Saccharomyces is Newtonian, okay, and Strepto, this one. Again, you can notice that the culture of the most of the bioreactor is not the Newtonian one. This is how we measure the viscosity, okay. And one thing that we talk about this one, okay, if you change the particle inside, you change the viscosity. This one is summarize how you're gonna affect the viscosity inside. So you have different cell concentration, you have different cell morphology, okay. Sometimes it's not the same. Cell 1, 2, 3 is about the cell. You have different osmotic pressure inside. You have different kind of polymer, and you have the rate of shear is different. Shear rate is different. So this thing can affect the viscosity inside culture medium. But you might have the idea already. This one is just select from our book, so you can have a look again on the book. And the next part is we will talk about the mixing after we know about the fluid, what is non-Newtonian, Newtonian. So, and this is Leno number. This slide is very important, this one. And inside the bioreactor, we can talk about the fluid mixing. We have function of mixing equipment, pattern of the stir tank, mechanism of mixing, how we gonna assess the mixing property, okay, and how we gonna scale up the mixing. And actually the summary is inside the book already, but what I talk today is about summary, okay. This is again content for this one. How we gonna improve the mixing. Mixing is very important inside bioreactor because if you cannot achieve the good mixing, sometimes the property is different, and then you cannot get your product as you desire, okay. This is function of mixing. Mixing is a physical operation. Even though it's physical operation, so it's very important, as I mentioned before. You can eliminate the gradient of concentration which is mass transfer, temperature, which is mass transfer, or other property. Sometimes this is kind of involved. Sometimes you need to mix medium, which such as sugar, for example. You disperse the gas through the liquid to form a small bubble to give a very good mass transfer, and you suspend the solid inside. Solid, you can notice that is a cell, for example. Disperse immersed liquid. Okay, sometimes you just mix everything together. Promote heat transfer because you want to remove some heat from your system. Mixing is really important, even though it's what is called physical operation, but still again it's very important. This kind of this thing is what is called normal stir tank bioreactor. You have the mixer, which is impeller, this one. You have a sparger, which is something that you put the air inside and then you sparge the air. This sidebar is baffle. This is function of baffle. So if baffle is something that you what is called, it's barrier for the moving. So it can cause the mixing here. See, if you don't have the baffle is this one. Sometimes you don't have the barrier to protect the fluid, so it cannot promote the mixing inside, and you have different configuration of the baffle here. So sometimes it depend on your design. Okay, this is a stir tank bioreactor, and then you have baffle, and then you have a chart like this to mix everything. This is equipment, and sometimes you have different shape of the bottle. Okay, and this one you cannot have the flat one like this. Sometimes you have this one A, B, what is it say, flat. Dish is something round here, round, okay, more round than B, and then we have contour, boop, boop, like this. This kind of thing is just try to promote a mixing. Cone and leaf, okay, and then this one is a conical, the F1. Okay, this one we just try to promote mixing. This is the round of your this one. It depends. Now we have different kind of thing. This is more B and C is more what is called, you might see in the real life or in industrial. B and C is more common. Okay, this is a specification for the stir tank. So we have this one, buffer clearance, DBF. DBF is this one, this space here. It's not stick together, but it's you have some space here. H1, liquid height. Liquid height is not all the height that we have inside the reactor. Sometimes we have 80% of the height. Okay, you don't need to fill everything here. You just liquid height here. Braid length, this one. WD, okay. Braid width, braid baffle. Even braid had their own baffle. Okay. CI is what? Impeller clearance, this one. This is a spatula diameter. Tank diameter is this one. How we gonna decide this one? So in the book they have the dimension. Sometimes it's related to this diameter, okay, and then the number will come up. It depends on the volume that you need. Okay. And when we talk about the dish here, the braid, we have different kind of what is called the impeller design. See, this one is SIG braid, dish turbine. We have this kind of configuration. This one is called propeller. This one is called turbine. See, different things. This one is anchor. It's like the one that you put, similar to the one that you use on the boat. Gate anchor is this one. Helix screw. Different type of impeller is depend on the, again, viscosity of your of your fluid inside the bioreactor. Okay, you just choose first. Look at the viscosity first. Is the unit is centipoid. Okay, and then you choose the. You can see the helix one is more viscous fluid. A popular is more range here. Okay, and you can imagine that most of the fluid or most of the liquid is a property of water, so you can check again what is the property of water that you use inside. Okay, pattern of the stir in the tank. See, this one is something that you don't have the baffle. Baffle is this one that I mentioned. Okay, see, you don't have the barrier. It can call this curve thing. This one is called vertex, and then you have nothing to promote mixing here. But once you have the baffle, something happen differently. See, the pattern of flow is different, and you have this kind of flow and you have this kind of flow different. And again, most of the industrial CSTR or continuous stir tank bioreactor, you need to have the baffle. And you have two kind of pattern: radial, this one, and axial is this one. Okay, and this is different turbine can different impeller can promote different flow like this. Okay, for example, this is axial, this is radial. Okay. And mechanism of mixing is turbulence is very important inside the system. Turbulence can be promote the mixing. Okay, we have three types: distribution, dispersion, and diffusion. Distribution is some call is macro mixing. Macro is mean big. Diffusion is micro mixing. Dispersion is classified either as micro or macro. Okay, differently. Distribution is bigger distribute of the particle. Diffusion is something smaller. You diffuse this the concentration. Dispersion is something between these two. Continue. We have different term here. eddy is rotation of the flow. Okay, it's called eddy. Where is it? Eddy. We don't have eddy here, right? Okay. We don't have eddy here. It's something like very small, like this. Like this. It's called very small swirl here. It's called eddy inside the fluid. Okay. For that one. Small eddy is called dispersion. Okay, eddy is called small dispersion. Dispersion. The process of breaking up bowel fluid into small and small eddy. Okay, this one is what I mentioned before. It's called eddy. This small pattern here is called eddy, and the mechanism that flow break into small eddy is called dispersion. Okay. Okay, something like that. One parameter that we can determine how good of the mixing is, we call it as mixing time, TM, mixing time. Again, time is mean okay, which how long that you're gonna take from your very good homogeneity or good mixing already. Okay, this is how we will measure how good of our system has the mixing time. Okay, that why is very important. So we have the example here: fermentation broth, which is viscosity of this one 10 to the minus 2 p pascal second. Density is this one is similar to water, 10 kilogram per cubic meter aggregator in this is volume of the stir tank. They use Russian turbine with diameter of 2.5 m, which is the speed of this one. This is speed of the stirrer, is 1 per second. We just estimate the mixing time. Russian turbine, what is this one? This one. Russian turbine is this one. They use this one, okay? And pitch bed is different one, right? Russian turbine is something like you have this kind of 90 degrees to this kind of dish. Okay, this one has 6. They have different number as well. This one, Russian turbine is this one. Okay. We try to find the Reynolds number, okay, from this equation again. This one, okay, the speed time what? Diameter square, okay, speed time diameter square time density and over viscosity, which is this one. And again, you have dimensionless number. You have dimensionless number, okay. And for this equation, you have a look on equation 7.16, okay. And you have this one. Mixing time is 1 point what is called, this is speed, right? Okay, mixing time, this is speed, okay, and this is number 1.54, okay, and this is volume, this is diameter, okay. And you have a look on this equation again. Okay, you can imagine how we gonna determine the mixing time. For this one, the mixing time is around 33 seconds. Okay, it means that you need 33 seconds at least to mix everything inside this system. So you have roughly idea how long you're gonna let your reactant to be inside this one. Is quite fast, right? It's less than 1 minute. Okay, and we continue with the, as we know that we need to have this stirrer here, and we need to put power to make it move, right? And we have this Reynolds number again. Its Reynolds number depend on your stirrer, and this number is NP, and there are different pattern, laminar, transition, and see, less than 10 is laminar, and then between is transition, and more than this one is turbulence. Okay, we need to have this kind of number to look at the power required for the system. And this is the number. Again, this is the suggestion for your design. If you need to design something, okay, again, impeller depend on your viscosity, so you can choose which one that you want to work on, and then how many, and then this is roughly the design of your system. Okay, we have a look on this example. We want to calculate the power required to put or to feed to your stirrer. Again, viscosity mu, density. This is the volume, baffle. Baffle mean the tank with the baffle. Marine propeller. Marine propeller is this one. This one, propeller. This one. Okay. Calculate the speed of this one. This is Ni. First, we calculate the Reynolds number. Reynolds number is turbulence. See? Reynolds number is turbulence. Okay. And then we find the NP is 0.63 using this table. Okay. And you need to refer to the book that I give to you. And then again, power is kilowatt. We change the unit here. And again, for this system, you need to put at least 83 kilowatt to your stirrer to make it move. So how this is important, because sometimes you need to spend electrical bill to feed your system. So you know exactly how much you need to feed to your stirrer. Okay, how we gonna scale up the system? Okay, roughly is under turbulent condition. Most of the bioprocess, we want the turbulence condition because we want a good mixing. The power is this one. Per unit volume is proportional to fluid velocity square. Okay. If we want to have more velocity, and we put more power, for example, but again, it's over the volume. And what else? And this one is if you put the gas inside the system as well, like this one, you put the spatula here, you put air inside the system as well, and then is come up with this correlation. Okay, you have a look on your book. Again, Ni is speed, Di is diameter. I'm not sure about the Di. G is gravitational. This is some number as well. Okay, you can have a look on this one. But again, it's depend on the correlation, mean that is depend on the experiment. We need to check again our system is suitable or not. And how we gonna improve the fermentation? Okay, first thing, put more power. Okay, change the configuration of the system, install buffer, or maybe we put more impeller. For example, if your system is very large, so you put more impeller, like this one, multiple impeller. This is power required, right? Time power 1. Okay. Power dispersion. Okay, for this example. And again, we don't want this stagnant zone inside the bioreactor. This one is no mixing at all. It's called stagnant zone. We don't want this one. Even though with this one we have two impeller here already, we still have this zone. And something that affect the property of the mixing, this is this one. The average shear rate in a stir vessel is linear function of the stirrer speed. This is stirrer speed. This is a shear rate. Okay. As I mentioned, is most of non-Newtonian fluid in the bioprocess are pseudoplastic. Okay, because the apparent viscosity of the fluid depend on the shear rate. Okay, and then this is function of the shear rate is function of the speed. From you can have a look on this one, but it's very old journal, but still very famous. And the role of shear in the stirrer fermentation. Several mechanisms have considered in the term of their contribution to cell damage, because we don't want cell to be damaged, because It means that we cannot have good productivity if the cell is damaged. The cell damage is depend on the interaction between cell and turbulent eddy. Eddy is this one that I mentioned before, the small flow pattern here. If your cell contact eddy, sometimes it cause some problem as well. Wait, and correlation between the cell with the impeller, something that you contact with the system. Cell with stationary surface or with the wall, for example. Generation of shear force in the boundary layer near solid or near reactor, especially the one that near your impeller. Sometimes some configuration of the fermenter, they don't have impeller to protect the shear rate as well. Sometimes it's generate force by the bubble rise, and for example, okay, if we put the bubble here like this one, you generate some force here as well, like this one. And for that contact to the cell is cause you the damage to the cell. This is example already that how you gonna prevent your cell damage in your system. So is can be contact with if you have large turbulence, so your cell can be damaged. And if you have contact with the cell itself or the cell or the bioreactor wall, or sometimes it's near the impeller, or sometimes it's near the bubble, it can cause a cell damage. Okay, I think for the next part I might split into another video, so you can have a look later, I think. And I think for this one we just talk about the fluid mechanics and the mixing. So I think we can continue to the next section in the next video. See you again and enjoy the bioreactor class. For today, just bye bye.